All right, welcome back, everyone. We're going to wait a few more minutes, I think, just to let everybody get on following the break. All right, good afternoon, welcome back. Before I mention the next talks, Yager or Steve, do you have any announcements or anything that needs to be made?
No, go ahead.
All right, for the afternoon, we have two presentations, and then we'll have an update from the co-chairs followed by a discussion. And so our first presentation for this afternoon is Steve Yager. Go ahead, Steve.
Okay, thanks for coming back. I'm going to present some work coming out of IHEST, the International Laboratory for High Resolution Earth System Prediction. And we've recently completed a set of initialized decayal hindcasts at eddy resolving and tropical cyclone resolving resolution in the ocean and atmosphere. And these simulations were carried out on the Texas Advanced Computing Center facilities. So I wanted to start off just by setting some context as far as the state of where decayal prediction is these days. And for that, I'm going to show you some results from two of Doug Smith's papers. This is a 2019 paper in which he analyzed a full set of CMIP5 DCPP hindcasts. So he bundled 8 systems together, giving a total ensemble size of 71 members. And this is a plot showing the total temperature skill, precipitation, and pressure skill. I think these are annual fields for forecast year 2 through 9, correlations over this late 20th century period. And then on the right is the impact of initialization. So he contrasted this skill with a multi-model set of uninitialized projection runs. And the main takeaway here is that for near-term 5 to 10-year climate outlooks, initialized decadal prediction ensembles show robust skill improvements over uninitialized projection ensembles. And there are some regions where that's not true. There's some degradation in these blue regions, but on the whole, we can say that initialization is giving us more accurate near-term climate outlooks. And then he followed that up with this, this significant 2020 paper in Nature, in which he now combined CMIP 5 and 6 DCPP hindcast sets, giving a very large ensemble of close to 170 members. And the point, or the main takeaway from this paper, was that consistent with seasonal prediction, signal variance is too low in DCPP systems. And by signal, I mean the forecast ensemble average, which includes both the response to forcings and predictable internal variability. And as a consequence, very large ensembles are needed to achieve skill for atmospheric variability in particular, and this has become known as the signal-to-noise paradox. And I'll just walk through these images because these will be some of the metrics I'll be looking at as well. So ACC is the anomaly correlation coefficient that's shown on the left two panels here. The top left shows the full 170 member skill, and then the bottom left shows subsampled 10 member skill. So you can clearly see that for DJFM sea level pressure on decadal timescales, it's a strong function of ensemble size, and we can enhance the skill considerably by throwing more members at the problem. The mean square skill scores here on the upper right, this is a metric that varies between -infinity and 1, with 1 being a perfect prediction. And this measures, it's a normalized measure of the forecast error variance relative to observed variance. And so this gives an idea of the forecast anomaly magnitude and how well the prediction system is getting the magnitudes correct. So you can see in this multi-model ensemble that a lot of these regions of high ACC also are showing positive mean square skill score, although in the North Atlantic in particular, it's close to 0. And then the RPC is this metric on the lower right here. The RPC is the ratio of predictable components, which is a metric that the Met Office has introduced. And this varies between 0 and infinity, and the ideal prediction system will give an RPC of 1. And so what this measures is the ratio of the observed signal to total variance divided by the model signal to total variance. So this should be 1 in a perfect prediction system. And we don't know the real world signal to total ratio, and so we approximate that by the anomaly correlation coefficient that we're able to achieve with the prediction system. And what we see in this analysis is that this region of high sea level pressure skill in North Atlantic is characterized by RPCs much, much greater than 1. And so this is indicating that there's a significant signal to noise problem in these hindcast ensembles, suggesting that the real world is more predictable than the model. So the real world predictable variance fraction is higher than the predictable variance fraction that we get from these model ensembles. And this has spawned quite a literature recently with many people reporting the signal to noise paradox in prediction systems and coming up with hypotheses for what could explain this. This is an important problem because the prevalence of unrealistically low signal to noise in CMIP class models has significant implications for coupled model fidelity, both response to external forcings and propagation of internal variability through the coupled system. So in the CESM world, we have the Decay Prediction Large Ensemble using CESM1. This was a 40-member ensemble. And several papers have shown that there's high decadal skill for some atmospheric fields, but generally this high skill is always accompanied by RPCs greater than 1. So here's an example on the upper right from this BAMS article in 2018, showing the anomaly correlation for summertime precipitation with this high skill over the African Sahel region. This is for forecast year 3 through 7. If you look at how that Sahel precipitation skill varies as a function of ensemble size, the red curve shows the correlation with observations. So it's asymptoting after about 20 members and giving a net score of close to 0.8. And the orange curve here is the model ensemble mean correlated with individual ensemble members from the hindcast set. And that's lower than what we're achieving when we correlate with observations. And so this is suggesting an RPC for this particular quantity of interest of about 2. And also for decadal winter NAO, this paper showed that DPLE does have quite high skill, correlations of about 0.6 for lead year 2 through 9, I think, winter NAO. And again, the dashed curve here is the model trying to predict itself, which is quite a bit lower by a factor of about 5. So the CESM system is certainly characterized by this signal to noise paradox. So some of the motivating questions for looking at high resolution decadal prediction, are how does decadal prediction system performance change with mild horizontal resolution? Does resolving mesoscale air-sea interaction help to address the signal to noise paradox and initialize climate prediction? And what are the predictability limits for regional scale climate extremes like tropical cyclones, atmospheric rivers, et cetera, on multi-year to decadal timescales? And in this talk, I'm just going to give a preliminary answer to the first 2 questions. So first, why might we expect improved representation of mesoscale air-sea interaction to help resolve the signal to noise paradox? Well, there's a lot of literature, a lot coming out of NCAR showing that the atmosphere responds to ocean mesoscale SST forcing. Here's a plot from one of Justin Small's paper. It shows the simultaneous correlation of latent heat flux with SST from observations, from high resolution CESM, and then from low resolution CESM. So we can see that when we move to eddy resolving ocean with an atmosphere that can feel those eddies, we get a positive correlation between SST variability and latent heat flux, suggesting that ocean is driving the atmosphere, particularly in these regions of high eddy activity in the western boundary currents and in the equator. Furthermore, coupled climate simulations with eddy resolving ocean, nominal 1 degree, 0.1 degree, are qualitatively different from and generally more realistic than those with coarse resolution ocean, nominal 1 degree. And there's a growing literature on this, although long coupled climate simulations at this resolution are still rare. A lot of the work coming out of IHESP is showing that there's clear differences and generally more realistic coupled behavior in these high resolution coupled runs. And finally, a lot of the work coming out of Ben Kirtman's group has specifically focused on the question of decadal predictability and signal to noise. And they've shown that these signal to noise ratios are too low in current CMIP class coupled models and appears to be enhanced in coupled simulations with high resolution ocean. So there's good evidence that moving to high horizontal resolution will help to address the signal to noise issue, but no definitive evidence yet. So here's what the high resolution decadal prediction system looks like in direct comparison to our DPLE system using CESM1. So we've got a slight change in model version. The main difference is this change in horizontal resolution in the atmosphere and ocean components and corresponding changes in land and ice. Slight change in the CAM from finite volume to SE dicore. There's also been some subtle changes in the way that we initialize high-res DP. So in DPLE, we used a 1 degree forced ocean sea ice simulation to initialize the ocean and ice. And in high-res DP, we're using same technique, but with a higher resolution ocean and a different forcing data set. We're also initializing the atmosphere and land in this high-res system. We've got far fewer start dates. We're only able to achieve 18 start dates every other year from 1982 to 2016. And we're only running these out 62 months, so roughly 5 years, as opposed to 10 years in DPLE. And we can only afford a much smaller ensemble size. But we can correct for these differences in hindcast start date and ensemble size. And our contention is that these other differences are relatively minor, and that if we contrast high-res DP with DPLE, the most important difference is the horizontal resolution in the ocean and atmosphere components. We can't prove that, but that is our contention. So let's move on to results. First, I just want to show you what this system looks like in terms of one quantity here, subpolar North Atlantic SST. The black and gray curves here show different observational estimates of this multi-decadal variability in subpolar North Atlantic SST. And then the orange curves show the FOSSI simulation that's used to initialize the different systems. On the bottom is DPLE, on the top is high-res DP. So first we can already notice that high-res DP wasn't quite able to achieve the matched observations in terms of our FOSSI simulation. So we have this early warming in the 90s in high-res DP that we don't see in the FOSSI used for DPLE. And then we can also see that when we initialize these hindcasts, we get a cooling drift in both DPLE and high-res DP. And that drift appears to be more pronounced in high resolution than in low resolution. Through the magic of drift correction, we take away a lead time dependent climatology, and now we start to see some good resemblance between our hindcasts and these different observational benchmarks. Again, we see perhaps an early warming in our hindcasts that's associated with the early warming from the FOSSI simulation. So there are some flaws that we have yet to understand in high-res DP compared to DPLE, particularly in the high latitude North Atlantic. All right, so this plot now shows the anomaly correlation coefficient for surface air temperature, no detrending. 10-member high-res DP on the left, 40-member DPLE on the right. We're verifying against crew TS observations over land, HAT ISST over ocean. We can see that these two systems exhibit very similar ACC patterns, and external forcing is probably contributing significantly to skill in both systems. So what we want to do is take into account this larger ensemble size. So we can subsample DPLE and look at the mean skill of a 10-member DPLE system and compare that to the 10-member high-res DP system. And then at each point in space, we can assess whether high-res DP is more skillful than DPLE based on this large distribution of 10-member skill scores that we can generate. And so my labeling here is the open circle means that we have 90% confidence that high-res DP is more skillful than DPLE and vice versa for the closed circle. So what you can see is the prevalence of open circles here, showing that we've got high confidence that the high resolution system is more skillful than DPLE after accounting for ensemble size. And there are some exceptions. So Canada, North Atlantic, as I mentioned, is a region where we appear to be doing worse. And then the Indian Ocean is another region of skill degradation. We can also look at the mean square skill score. So how are the magnitude of predicted anomalies comparing to observations? And again, we see a prevalence of these open circles showing that high-res DP has a higher mean square skill score than low-res DP over most of the globe, with some exceptions. This plot shows the same set of metrics, but now for annual precipitation. So pentadal mean precipitation anomalies verified against crew data over land and JRA 55 reanalysis over the ocean. And the takeaway message is that high-res DP has higher skill over much of the globe. It's not quite as compelling as the surface air temperature comparison, but we can see by eye that most of these skill scores are higher in HRDP than in DPLE. But I want to end with this analysis of wintertime sea level pressure. And here's where we really see dramatic skill improvement by moving to high resolution. So here's the 10-member DPLE skill score showing kind of low level positive ACC. And we see this huge improvement in our ability to predict pentadal variations in winter sea level pressure over most of the globe, in particular in the Eastern Pacific and Northeast Pacific, but in other regions as well, including over Greenland. But the North Atlantic is in general a region where we're not seeing any improvement. And we see that both in ACC and in mean square skill score. So as I showed before from the Doug Smith paper, this ACC for sea level pressure is quite sensitive to ensemble size. So with a 40-member DPLE, we can enhance that skill and get ACCs that are roughly commensurate with the high-res DP results that we're getting with 10 members. And so if we look at the ratio of predictable components, this measure of whether there's a signal to noise paradox in the system, we see this prevalence of values much greater than 1 in DPLE wherever we have high skill. But that's in stark contrast to high-res DP where we're getting high skill with RPCs that are close to 1. And these values for DPLE would be even higher if the ACC from high-res DP were used. I'm actually using ACC from DPLE. And as I mentioned, this is an estimate of the observed signal to total. It's a lower bound. So we don't know what this is. And if a system can get a higher ACC, then we should use that as our estimate. And finally, this signal to noise ratio improvement is associated with much stronger signal in the high-res system. So if we look at the signal to total ratio, it's much higher over these regions where we're seeing high skill. To summarize, IHESP has completed a set of initialized decay prediction hindcasts, unprecedented high horizontal resolution. We've completed a first set, 18 start dates, 5 years, 10 members, and that's enough to permit drift correction and skill assessment over this late 20th century period. A compute proposal has been submitted to further expand the set. We're finding that high-res DP yields significantly higher skill than DPLE after adjusting for ensemble size, for pentadal climate variability over much of the globe for surface climate fields, and sea level pressure in particular shows large skill improvement. In many but not all of the regions, high atmospheric skill and high-res DP is achieved with RPC around 1, and that's due to the large signal variance in the system. And that's in contrast to DPLE, where high ACC is generally characterized by RPC much, much greater than 1. And so I think this is the first demonstration from an initialized prediction system that increased horizontal resolution can help alleviate the signal to noise paradox. Thank you.
All right, thanks, Steve. Any questions for Steve? You can either put it in the chat window or raise your hand. Sanjeev?
Yeah, thank you, Steve. This was great. You kind of touched on this issue. Since the SLP is showing the higher that the signal to noise ratio paradox, so that's why you got that improvement in the SLP compared to the temperature. Temperature was not showing from the starting itself that RPC values significantly greater than 1. That's why you didn't get much improvement in the temperature. So RPC by itself is a variable dependent or variable of your interest.
Yes, I agree with what you just said. I'm not sure where the question was. Certainly RPC varies from field to field, and sea level pressure, atmospheric circulation is one of perhaps the field where RPC or signal to noise issues are most identified, not so much in temperature. And that's consistent with Doug Smith's paper as well.
Thank you.
Judith?
Yeah, thanks so much. Very interesting. I would like to listen to it 2 more times before asking my question, or maybe it's a comment. So I have not completely understood this RPC metric, because it has to do more with variability than actually something like rank probability skill score or spread, as we do in initialized forecast in the atmosphere. I wanted to alert you, there's a large body of work which looks at blocking in the atmosphere. And with blocking, it is that models can't capture it. And if you go to either high resolution or you go to stochastic parameterizations, models seem to have much better blocking, which has effects on predictability for especially over land, right? Because blocking can give you additional predictability. I don't know if some of the lessons that are learned in the atmosphere can be applied to this, because it's sufficiently different, but it has to do in that particular case with subgrid scale noise. You need to have a certain high resolution component for blocking to be maintained in those models. So maybe we can talk more if it makes sense for the ocean as an explanation.
Yeah, and you might have noticed that HRDP didn't solve everything everywhere, and the North Atlantic remains a region that's difficult to predict, even with an eddy resolving high resolution atmosphere system. And so some of the things that you mentioned, could be really important for that region in particular.
Andrea?
Yeah, Steve, my question is a little sort of half-baked as I'm asking it, but I'm wondering if I could get you to just think about this a little bit. This thing of reducing the noise at higher resolution, and so the signal to noise, is there something baked in there that necessarily at higher resolution you're going to find that the noise, I'm trying to articulate the question well, but I'm wondering if there's something that this is what had to happen when you go to higher resolution based on the metrics that we're using for the noise. Is there something inherently baked in there? That's my question.
I don't think there's anything baked in, but I think these results do raise a new paradox, which is by increasing noise in the system, by having an ocean that has weather and eddy noise, you're essentially reducing the signal to noise problem. And that's hard to understand how that works. But I think it has to do with the literature on ocean mesoscale forcing of the atmosphere. So we've got predictable signals in the ocean that are low frequency, and they imprint on the atmosphere through ocean eddies. And that's kind of my half-baked answer to your question.
All right, I think it's, I don't see any other hands up, and I think it's time for us to move on to the next talk. Thanks, Steve. Our next talk is from Jerry Neal.
Okay, hang on just a second. Okay, let me just put this on here. All right. So I wanted to acknowledge my co-authors on this work, and there's a list of them there. And this all kind of started around the time of the IPCC Era 5 in 2013 and extended for the next couple of years. And there was this debate on whether global warming had either stopped or slowed down. And that's because the trends in global average temperature increase seemed to have slowed down in the 2000s. And Tom Carl and other collaborators came out and said, no, the big story here is the long-term externally forced trend. And if you drew a trend line from 1950 up until nearly present, that's the big story. But another interpretation represented, for example, by the Fife et al. Paper and others was that, yeah, the trend is there, the long-term forcing trend, the long-term trend is there from external forcing, increasing greenhouse gases. But superimposed on that are these interesting decadal timescale variations of global average temperature, and those seem to be tied to the phase of the interdecadal Pacific Oscillation in the tropical Pacific, such that these red trend lines are when the IPO is in its positive phase, and the blue trend lines are when the IPO is in its negative phase. And there was, when you look at it in that frame of reference, you do see a slowdown on decadal timescales. And this, of course, has become somewhat of a moot point, because since then, we have seen a resumption of larger rates of warming, and you get this kind of view of negative and positive IPO associated with different magnitudes of trends in global average temperature. And implicating the tropical Pacific in this was this paper that Kasaka and Shi published in 2013, where they were the first to use the so-called pacemaker methodology, where you specify time evolving sea surface temperatures in the tropical Pacific in a model that's fully coupled up everywhere else. And they were able to show that by doing this, the tropical Pacific SSTs being specified to observations in a time evolving way, the orange line, you can kind of recover this slower rate of warming, which is the black line in the observations, as opposed to a model that's fully coupled everywhere that just kind of had warming going on everywhere. So it seems like the tropical Pacific was playing some kind of a role in this. And then the question was, well, does any model actually show this? We looked at the CMIP5 data and looked at 262 ensemble members and asked the question, were there any ensemble members that could get this slowdown of the observed warming that we saw in the early 2000s? And it turns out 10 members out of 262, this is the red lines here, were able to get the observed slower warming trend. And of course, this is a rare thing to have happen, 10 out of 262, because the randomly generated internal variability of a model simulation has to exactly match the randomly generated internal variability of observations. That happened to occur 10 out of 262 times, but when you composited those 10 ensemble members, you recovered this negative phase of the IPO, again, bringing this back to what was going on in the tropical Pacific. So when we were looking at decadal time prediction, you hope that there are some mechanisms and processes that are in the system that if you initialize them in the right way, you may be able to get some predictability out of it. And we also realized that we can use these initialized hindcasts to provide insights into these processes and maybe point to further analyses to increase our understanding. And we're going to be looking at the IPO here. And so the IPO, of course, just to review this is kind of a typical IPO pattern, which in this case is represented by the second EUF of low-pass filtered sea surface temperature from observations. It has this PC time series, which is sometimes used as an index for the IPO with its negative and positive phases. And we care about this because if you correlate the IPO index with the low-pass filtered precip, you see areas of increase and decreased precipitation on decadal timescales over land areas where people live. So suggesting that we may want to be able to predict things in the ocean associated with IPO, because it does have effects over land. If you start looking at these initialized hindcasts, in this case from the DPLE that Steve was just talking about, and you look at these off-equatorial West Pacific boxes for ocean heat content, you see this interesting low frequency variability, such that you kind of have large values in both the north and the south box around the time the IPO went from negative to positive. It's kind of smaller values when it went from positive to negative, larger values when it seemed to go from negative to positive again more recently. And the intriguing possibility or association here is that these transitions occurred around times of significant ENSO activity. So the 72-73 ENSO event was right around the time of this transition. The 2-year 98 to 2000 La Nina was right around this time of IPO positive to negative. And the big 2015 to 2016 El Nino right around the time of this possible transition of the IPO from positive to negative. So let's look at these initialized hindcasts to see if we can get some insights into the physical processes. Now, this is a version of the figure that Jean showed this morning, and this is now from the more recent model, the CESM1, the DPLE. This is now looking at initialized hindcasts for lead years 3 to 7, so the 5-year averages, and we're looking at the metric is pattern correlations over the Pacific Ocean for these time periods. And we calculate these pattern correlations such that obviously the higher the number here, the better the hindcasts. And we calculate anomalies from which we calculate or compute these correlations in 3 different ways. And I don't have time to talk about that, but The story here is that no matter how you calculate anomalies, all these three lines, the colored lines are higher or high during these time periods of IPO transition. IPO transition are these kind of gray vertical lines here. So you have relatively high pattern correlations right around the times of these IPO transitions. We have really loss of skill in this in the Pacific associated with Pinatubo that Jean was talking about this morning, and also with Verver and Nabro more recently, and that's the topic of another talk. But we're kind of, it's intriguing that the hindcasts seem to be able to get some of these processes. So what can we look at? Let's look at a couple of older papers here. This is a paper we published in 2014, an old model, CESM1. But the same kind of idea, we looked at the 3 to 7 year lead prediction for the years 1998 to 2002, initialized in January of 1996. And this is, again, for the transition from positive to negative IPO. So this is the prediction here for negative IPO, and this was the hindcast for that same time period. It's not nearly as strong. It's kind of going in the right direction. You get a pattern correlation of 0.6, but it looks like it's trying to do the right thing, and it's quite different from persistence, which persisted the positive phase of the IPO, and from the uninitialized, which is just the externally forced trend with warming everywhere. Now, the interesting thing about this was that for this time period we're trying to predict, if you look at Nino 3.4 SSTs, the black line is the observations that showed this 2-year La Nina, and the red line is the ensemble average from the hindcasts, also showing not quite as strong a 2-year La Nina, but definitely below normal SSTs in the Nino 3.4 region. And again, this makes you wonder, could INSO events trigger this transition or play some role in the transition of the IPO? Let's look at another published hindcast or prediction here. This is now for the model initialized in 2013. It got a small El Nino event here in 2015-2016, which was just starting when we were publishing this paper. Mark Kane actually urged us to publish this prediction before it was actually going to verify, just for fun. This is our prediction showing kind of a positive phase of the IPO for the year, for the time period lead years 3 to 7, for the time period 2015 to 2019. Quite a bit different from persistence, which was persisting the previous phase of the negative IPO, and different from the uninitialized, which was just the free running model showing the externally forced trend of warming everywhere. Significantly, you can see that the trends of global average temperature over this predicted period for positive IPO were roughly 3 times higher than the trends over this time period in the early 2000s. So that seemed to be consistent with previous things we saw in the observations. And just to see if this actually verified, now this is looking at the DPLE, which is a different, more newer model, but same kind of idea. This is the DPLE initialized in 2013 for lead years 3 to 7, 2015 to 2019, showing this positive phase of the IPO. And this is kind of what happened in the observations with pretty high pattern correlations, and quite a bit different from persistence, which was persisting the negative phase of the IPO. So given these results that we've seen from the initialized hindcasts, we can hypothesize maybe that when you get this decadal timescale buildup of off-equatorial Western Pacific Ocean heat content, and when it reaches some kind of necessary threshold, then interannual timescale INSO activity could contribute to a transition, kind of like a subseasonal westerly wind burst event can contribute to a transition of an interannual El Nino event. So we're going to look at a long pre-industrial control run with CESM1, 1800 years. We compute the IPO index and select IPO transitions based on this index. We get about 50 of each, negative to positive, positive to negative. We're going to composite those transitions. So this is now some of these composites. This is going from negative to positive IPO. The blue line is the IPO index, which we defined a transition as when this index crosses the 0 line. And you see that the off-equatorial ocean heat content anomalies in the Western Pacific are positive leading up to this transition, and then start to become depleted after the transition. And from positive to negative IPO, same kind of thing, but kind of the other sign. Positive to negative IPO is the blue line going from positive to negative. Off-equatorial heat content is negative before the transition, then starts to recharge. So the question is there a better chance of an El Nino event for a negative to positive transition than a La Nina? And sure enough, there is a better chance of an El Nino event occurring at this year 0, and actually in years around year 0 as well, compared to La Nina events. And for positive and negative, there's a better chance for a La Nina event compared to an El Nino event. So it does seem to be in this long control run that this interannual timescale variability could be playing some kind of a role in these transitions. How could this actually happen? Well, we can look at these composites now and zoom in on the Western Pacific, where we think that's kind of where things are happening. The black lines here are these boxes that we looked at for ocean heat content. The colors here are wind stress, U-component wind stress anomalies, and this is 4 years prior to a transition. And you can see the blue colors here indicate strong easterlies in the equatorial Western Pacific, and this is associated with the negative phase of the IPO. This is 4 years before a transition to positive IPO. So we have negative SST anomalies you could imagine in this area, and negative precipitation convective heating anomalies. You also have these areas of positive westerly anomaly wind stress around 20 north and 20 south, and looks kind of like a kind of anomalous gill type response to maybe a negative convective heating anomaly going on here in the Western Pacific. We can check that out by doing an atmosphere only simulation where we specify a negative convective heat anomaly here at 165 east, and that produces these wind stress anomalies with the same kind of color convention, strong easterlies in the equatorial Western Pacific, westerlies about 20 north and 20 south with this anomalous gill type response to this negative convective heat anomaly, producing those wind stress anomalies. And you can imagine those wind stress anomalies then would produce wind stress curl anomalies and Ekman transport anomalies that would want to converge heat into these off-equatorial boxes. And we can actually see that in this composite here. This is positive conditions 3 years before a transition from negative to positive. The colors are wind stress curl anomalies, and wind stress curl is an indication of how the wind stress is dynamically acting on the ocean. So blue colors here are where wind stress curl would be forcing water down into the subsurface ocean. And with the sign change in the southern hemisphere, red colors would be the same thing, where wind stress curl is forcing water down into the upper layers of the ocean. We still have the, I put on here the wind stress, surface wind stress anomalies with this kind of gill type response. The big arrows here are Ekman transport anomalies, so you get this kind of convergence of warmer water here in the off-equatorial Western Pacific, and that would increase the off-equatorial Western Pacific heat content anomalies. And this is the sea surface temperature anomalies associated with that negative IPO conditions 3 years before a transition. Now, at a transition, you say, okay, there's obviously in this composite, we're getting kind of an El Nino event forming here in the equatorial Pacific, and that would be associated with westerly anomaly winds in the Western equatorial Pacific. And the wind stress curl is already showing the possibility that we'd be having a convergence of heat into the Western equatorial Pacific, which would then kind of change the whole thing around, such that now you'd get downwelling Kelvin waves coming across the Pacific to deepen the thermocline. That would contribute to warming up the tropical Pacific with this kind of wind stress curl anomaly patterns. Now the opposite of what it was before. So this is 3 years after the transition. So now we're getting positive convective heat anomalies here in the Western Pacific with these positive sea surface temperature anomalies that would be driving a gill type response with cyclonic circulations north and south of the equator, and basically Ekman pumping. So you're bringing water up from the surface. This positive wind stress curl would indicate that in the northern hemisphere, negative, same kind of thing with the sign change in the southern hemisphere. So just to summarize this, these initialized hindcasts give us the indication that maybe IPO transitions could come about by the buildup of off-equatorial Western Pacific heat content that we saw in the ocean initial states for the DPLE, and that these transitions could be triggered by ENSO activities. So given that those kind of clues, we look at a long pre-industrial control run to see if we can document the processes a little bit better with more samples of these transitions. The results do show that these off-equatorial Western Pacific Ocean heat content anomalies are maintained by the SST precipitation and convective heat anomalies near 165 east in the equator. And in these composites, we see that El Nino activity can contribute to a transition to positive IPO if these heat content anomalies are necessarily large. So you can imagine that these conditions aren't going to be there every year, but over enough years, say over a decade or 10 or 15 years, you'd have enough of these conditions where you'd get enough heat that would be put down into the upper ocean and the off-equatorial Western Pacific to build up to the point where an El Nino could then trigger a transition. And that would then give you equatorial westerly wind anomalies, downwelling Kelvin waves that would deepen the thermocline further east. That would warm the SSTs across the tropical Pacific. Then you'd have positive precipitation convective heat anomalies near 165 east, as now you'd be transitioned into the positive phase of the IPO. And again, this is kind of analogous to other timescale interaction where subseasonal westerly wind burst events in the Equatorial Western Pacific can contribute to a transition to an interannual El Nino event. So I think the interesting bottom line about this is that the initialized hindcasts themselves can be used to identify processes that are important for predicting things in the climate system, like these IPO transitions. And at the bottom here are a couple papers where some of these results are documented. Thanks.
All right, thank you, Jerry. Do you have any questions for Jerry? Again, you can raise your hand or use the chat window, whichever you prefer. I have a question. I'm curious if you're kind of able to say that the initialized hindcast help you to separate the who's forcing or who's causing who kind of a situation here, as to like whether the ENSO may be causing changes in IPO or IPO may be causing changes in ENSO.
Yeah, well, that's of course the curse of a short record, right? Because we only have a limited period of the initialized hindcast, and we only have a limited period of observations. We only have several transitions of the IPO in this time period, and that's why we got these clues that this could be happening, what we were seeing in the initialized hindcast, and that gave us kind of the impetus then to look at the long pre-industrial control run where we don't have any external forcing. All we have is the model generating internal variability, and we get many more samples. So we get 50 transitions of each, as opposed to 2 or 3 in the initialized hindcast. And I think that's where you can really leverage these results from the initialized hindcast, is you get kind of indications of what the process could be, and then you can use that as a starting point to do some more analyses.
Yeah, thanks. I saw a hand up previously that disappeared, and I just want to make sure that person who previously had their hand up gets a chance to. And
yeah, it was Yoshi.
Yeah, go ahead, Yoshi.
Also, I have totally same question about causality between ENSO and IPO phase change, so ENSO activity. So, and I see you already answered, so I just lower my hands. Sorry.
Okay. All right. Great.
Thanks, Yoshi.
Yeah.
Yeah, Jerry, so this raises an interesting idea of forecasts of opportunity for IPO transitions, right? But as you say, the observed record is too short to really test that idea. But I was just wondering, you know, if you go back to your long coupled control run where you've identified these transitions and you did perfect model predictability experiments, would you, could you maybe say something about enhanced predictability with these precursors that you've identified?
Yeah, that'd be an interesting thing to do, depending on the RPC for the tropical Pacific. But that would be a possibility to look at that for sure. I don't know if anybody's actually done that for the tropical Pacific. I know people, Doug and others, have been doing it for the NEO in the North Atlantic, but are you aware of anybody that's tried this for the tropical Pacific?
No, not perfect model decay experiments, no.
Yeah, maybe worth trying.
But yeah, the problem with perfect model, of course, is that the models aren't perfect, and you've got these RPC issues, right?
Yeah, right.
I'm not seeing other hands, and we are stretching a little over time, but I don't want to cut anyone off, and if they have a burning question. All right, well, thank you, Jerry, and thank all of our speakers today. Before we move on to the co-chair report. All right, next, I think Yaga, are you leading the co-chair update?
I will start, and then I will turn it over to Steve. So I'll give a co-chair's update for the shorter time scales. And before I get into any simulations that we ran, I'd like to just thank Jim Edwards, Sasha, and Nan for contributing to running the large simulation sets that you'll see here. So they're not official liaisons for this working group, but they've been really giving us a big hand. All right, so here are the S2S updates. So firstly, there is a web page describing all the subseasonal hindcasts that we have, with links to where the data is, both on the Climate Data Gateway and also on campaign storage. And in case you don't know this already, the real-time forecasts are available both for CSM to CAM6 and CSM to WACAM6. and they go in this GladeP data share directory, so you do not need to have an account on Casper. There are instructions on the webpage above how to get the data here. So we usually run the forecast either on Tuesday night or on Wednesday, but they are always there by Thursday AM because that's when NOAA is picking them up for their outlook. Other simulations that we've done, so we've contributed to the WCRP Spark SNAPSI project, where SNAPSI stands for Stratospheric Nudging and Predictable Surface Impacts. And there is actually an article about the simulations in the geoscientific model development. More or less, there's a few sudden stratospheric warming events that were selected by the International Committee. And then we submitted simulations with a nudge stratosphere and both to climatology and then just free running experiments. So you can read about those there, and they are available on our system. ILA is still post-processing some pieces of it. Okay, and we also carried out some experiments to get to the source of where the predictability is coming from on the subseasonal timescales. I'm sure you've all seen this diagram that we know that ocean is more important on longer timescales, but it's a little bit important on that week 3-4 window, and the atmosphere and the land. So we've done experiments rerunning the entire subseasonal suite, where we put in realistic initial conditions for some of the components, and we changed some of them to climatology. So our first suite we ran was Clima Ocean. So atmosphere and land are realistic, but the ocean is climatological. Then we did a climatological atmosphere only for the winter season because the atmosphere seemed really important. So we thought we would completely lose predictability when we took that out. So I didn't want to burn too many resources. And we also have a suite where we have climatological ocean and climatological atmosphere. So only there is realistic land. So I'm briefly going to show you what those have shown. So here's our control week 3-4 skill over the globe. And here's Clima Ocean. So what you see if you compare the middle to the left, that there's actually very little loss of skill. And we also have another set of simulations where the ocean is shifted by 1 year. And we also found the same thing, that the ocean on the week 3-4 timescale, in our model, at least, it almost makes no difference. We could have put in something, anything really at the bottom and still retain most of the features of the forecast. Now, the atmosphere, as you can imagine, is a lot more important, but what's fascinating that it's important in parts of the world. So if you go to climatological atmosphere, you lose most of your skill over Europe and Asia compared to the full forecast with fully observed fields. However, in other places like South America, we still have really high skill. And a lot of the skill comes from the land, because when we change the ocean and atmosphere to be climatological, you still see almost the same scale as we did when everything was initialized from observations. So we're just beginning to analyze these runs. Here is JJA, and you see something a little bit different. So again, the ocean does not make a whole lot of a difference, but it does seem like over in North America, there is perhaps a greater impact. And on the right, you see the one there's only observed land. And you can see that a lot of skill, we can already just on the subseasonal week 3-4 time scale comes from that the addition of the atmosphere and land are much less important. So we've completed these experiments. The one you don't see on the list is Clima Land, as none of us, so Steve and I are not land people, and we've been having a hard time engaging a land person in our work. And it's not trivial to create climatological land initial conditions because several of the variables go deeper down into the land model. They're not the same across grid boxes. There's discontinuity. So if you would like to get involved, if you think such a suite would be of interest to you, please let us know and we would welcome the help. So we already have one person looking into MJO in these simulations, and Sasha and I are looking into the analysis. But if you'd like to get involved in these simulations, also do let me know. All right, a little update on the S2S diagnostic package. So this is effort led by Judith Berner and Abby J. So they have built on the ClinProd package, which is based on Python-based package. And I think at the last meeting that you were at, the package could calculate ACC, root mean squared error, and spread. And they have now added several new features to this package. So now it's doing ranked probability skill score, potential predictability, state dependent forecast skill, and statistical significance. So in these next slides, I'm going to show you a few figures Judith sent this morning. So it's DJF ACC for neutral P&A events, and on the right for negative P&A. And this is predictability in the left columns, lead 1, lead 15, and lead 31 days. And you see that there are quite large differences. So for example, for negative P&A, there is much greater skill scores than for neutral P&A. And similarly for lead 31. So that's quite a striking difference. And again, here, this is average over, I think it's over North America, and focusing again on weeks 3-4. For if you look at all the neutral P&A cases, ECMWF still has higher ACC than CSM2. However, if you look at negative P&A times, then CSM2 actually is able to outperform both the NCEP system and ECMWF, and you see that all the way out to weeks 5-6. And lastly, this figure shows you comparison between what you've seen before and also with the perfect model representation. And oops, I think I lost you. Hang on. Apologize about that. Get back to the right slides. So the scale actually, the perfect ensemble scale is a little higher in some of the places, as you see, compared to what you see against observations. And I think Judith Berner is on the line, so I will let her chime in a few words before we turn it over to Steve.
Yeah, so if you have any questions or if you want to use the package, that would be great. I still hope we will do some of these SMILE analysis with it. At least I know you have your own packages and stuff, but it would be nice to really try and do this in this Pangeo intended environment where people leverage what other people have done. This package was used by in the ASP Summer Colloquium, and if you're interested for S2S Science, all the lectures are now on the YouTube channel that is shown there, and we have a follow-on workshop that is in person, COVID allowing this year in July 11th till 15th. And it's mainly the same people, and the idea is that we want the students to get to know the speakers in person for cohort building. And so this group is still using this and developing the package, but outside we have no contributors just yet. And with this, I stop. And yeah, there's some questions. So I will hand over to you, Yaga, when you want to take them.
Sure. So Jerry has a hand up. You may as well take that now.
Yeah. Okay. So this looks great, Judith. You've got it set up for S2S, and you mentioned extending it to SMILE, but how about out to decadal? I mean, is it easily convertible to other timescales?
Yes. So this is a series of Python workbooks, and it is using that package Klimpret, which was developed by Riley Brady and Aaron Spring, and they were interested in decadal indeed. Some of the work mentioned before was done by them. So I think, so what it does a lot of stuff. It takes a lot of time in terms of pre-processing, which is taking averages, removing the drift, removing seasonal cycle, whatever you want. It should be trivial to make this useful for decadal. The one thing we think it will need some work is once we have unstructured grids. I don't know how much work it is to read in unstructured grids and process them, but we don't do zonal means, so that's not a problem at this point.
Okay, all right, thanks.
Yeah, I'll just mention that the package was actually initially, the Klimpret package was actually initially developed with for decadal prediction. and then has been extended to the S2S timescale. So it should be fairly easy to use it for whatever timescale you're looking for.
Okay, thanks.
Yeah, okay, if you're speaking, you're muted.
Sorry. Yeah, I just realized I was
okay.
Yeah, so we've heard about SMILE, and just to remind you what SMILE is, it's our new seasonal to multi-year large ensemble. These are seasonal to interannual hindcasts using the new CESM2 model with Marble ocean biogeochemistry enabled. So we're using 1 degree resolution in all components, low top cam, and we're running 24-month simulations initialized from observation-based states, which in the atmosphere is just a regridded JRA55 reanalysis initial condition. In the ocean and ocean BGC and sea ice, we're using our standard FOSSI simulation methodology using JRA55 DO forcing. DO stands for driving ocean. And this is the forcing data set that's been developed by Clavar's Ocean Model Development Panel for OMIT2 experiments. And in the land, we used a forced CLM5 simulation that used crew JRA-V2 forcing, and that's consistent with the trendy S3 protocol, for those of you who are familiar with that. So we've done 4 times per year initializations, the 1st of February, May, August, and November, 20-member ensembles. The baseline set is hindcasts spanning 1970 to 2019, and we've done some extensions through May of 2021, but these are, I would say, experimental because we had to change the method of generating land initial conditions. So we need to take a closer look at that before sharing these extensions. So I'm pleased to announce the SMILE public data release. You can find a link to the SMILE experiment off of our Earth System Prediction Working Group webpage, which is easy to Google. And so we've got our recent and notable simulations there. If you click on SMILE, this will take you to a description page with links to data that can be accessed directly on Casper if you have a Sizzle account. And we're working on getting this accessible through the Climate Data Gateway. That should be imminent, I would say, this week. I'm going to ask that everyone sign up on the SMILE analysis registry, which you'll find on the SMILE website, just so we know who's looking at SMILE and what their intended analysis is. A preprint of the SMILE overview paper will be available very soon. That hopefully will get submitted this week. And you'll also be able to find that on the SMILE webpage. So I thought I would just share some of the results that are going into the SMILE overview paper. These are not very in-depth. It's just meant to give a broad brush assessment of system skill and make sure that things are working as expected. This large multi-panel plot shows surface air temperature skill, no detrending. The columns show the different initialization months, February, May through November. And then the columns show the forecast lead time. So we're looking at seasonal anomalies as a function of forecast lead time out to lead month 19 on the bottom row. And what we can see is a significant prediction skill all the way out to this 2-year time horizon. 0.5, which is kind of a nominal measure of useful skill, is starting in the yellow color. So you can see that even at this 2-year lead time, we're getting some significant skill over land for seasonal air temperature. Now that's with the trend. So if we detrend, then a lot of that skill goes away, but we can still find some skillful prediction of deviations from a linear trend, even out to this 2-year time horizon, although skillful prediction over land is quite limited. Nevertheless, there's some interesting hot spots like the low latitude Americas, where we're seeing high skill, maybe not achieving 0.5, but suggesting there's potential here. and Southeast Asia. Where did I want to point for that one? I forget. Anyways, different regions are showing some interesting potential at these long lead times. Now, what's interesting is we can directly compare SMILE November to DPLE, which was also initialized in November. And these two columns show a comparison of surface air temperature skill after accounting for differences in ensemble size. So the rightmost column here is a 10-member DPLE compared, 20-member DPLE compared to 20-member SMILE. And what you can see by eye is that there's just general skill improvement in SMILE compared to DPLE. And this appears to be attributable to combined effect of model development. So CESM 1.1 lens used in DPLE, CESM 2 used in SMILE, as well as improved initialization. So we've taken care to initialize atmosphere and land in SMILE, and we've made some changes to the ocean and sea ice initialization as well. We can't say which of these is most important for explaining the skill difference. So in terms of ENSO, which is particularly important for prediction on these timescales, we find that SMILE skill for Nino 3.4 is competitive with the NMME multi-model mean. That's shown in this plot that shows the correlation for Nino 3.4. Blue is SMILE. The red dots show the NMME multi-model mean. So we're basically just as skillful as NMME, all models combined. And then the green dot here shows the ECMWF CES5 system at lead month 13. So we're just slightly lower than what they're getting with the ECMWF system. But our system goes further back in time, so we can look at things like ENSO skill dependence on the verification window. So the black curve shows the skill when you verify over the full time period, which is quite a bit lower than the 1982 to 2005 time period that is shown in the blue and red dots there. This is just to show that we're looking at all the different components of CESM2. So here's a result from the sea ice model. It's showing Northern Hemisphere winter sea ice extent on the left, and then summertime sea ice extent on the right. The blue curve shows the CESM2 lens, so the uninitialized 50-member ensemble mean. Black is the observations from satellite. Gray is the FOSSI that we're using to initialize. So we can see that the FOSSI already has some errors, although it shows a pretty good correspondence to observations. But biases in the initial conditions are particularly apparent in the summertime, where the FOSSI was not able to achieve this observed sea ice extent minimum in 2012. And so we're initializing from a flawed initial state there. And one interesting thing to point out is that the detrended skill is higher for JAS than for JFM. And finally, just to round it out, here's a result from the land model. This is showing terrestrial water storage correlation. This is at lead month 19, so for summertime, JJA. And this shows the correlation map across the globe. And then we're focusing in on this Southwest US region of high skill. If we look at the time series from that region, we can see this large low frequency variability in the initial conditions. That's the black curve. And then the SMILE hindcasts are shown in blue. So we're getting quite a bit of skill just from persistence of this low frequency variability in terrestrial water storage. Nevertheless, when we do the skill assessment, we find that our correlation scores for TWS of Southwest are consistently higher than you would get from a persistence forecast. So we're getting some additional skill by predicting the drivers of this terrestrial water storage variability. I wanted to mention that we're also generating CESM2 decadal hindcasts. So these are just extensions of SMILE November out to 122 months. So they're completely consistent with SMILE. They're just an extension. And so far, we've completed 10-member ensembles and the baseline set from 1970 to 2020. And so on the to-do list is to try to extend these backwards to 1958. So we've got a long verification window for looking at decadal timescale skill. And then if resources allow, it would be great to expand the ensemble size greater than 10. I want to mention some of the ongoing work that SMILE is already spawning. So here's a sensitivity study led by John Fasulo, examining the impacts of Australian wildfires. So what John and Nan have done is they've rerun the SMILE August and November hindcast initialized in 2019 using the GFED aerosol forcing through June of 2020. So rather than using the SSP 370 as in SMILE, we're using GFED that actually has the Australian wildfires in it, whereas the SSP data does not. So the comparison to the SMILE control then revealed the impacts of Australian wildfires. And John shared this fresh result, still work in progress, but what he's finding is that the difference between this Australian wildfires version of SMILE minus the control gives you this La Nina type response in the Pacific. And so they're planning a paper to document this, and once that is submitted, then I think these experiments will become part of the working group resources. And that's it for my update. I'll hand it over to Kathy.
All right, thanks, Steve. And I'd like to say, thank you to NCAR for providing these data sets. They're just such a rich resource, and certainly far beyond anything that any individual PI could do. And so as the university community representative on the ASPWG, I'm very grateful for these experiments. And really that's the focus of the rest of our next 20 minutes we have to talk about engagement and use of these data sets and the system. So I'm going to share my screen. First of all, I have a link to a Google Jamboard actually, it's doubled up there. Let's try it again without typing it twice. There we go. Link to Google Jamboard in the chat window. So go ahead and join that. And then I'll share my screen. And so if you're not familiar with Google Jamboard, I just want to make sure everyone understands how to use it. If you click on that link, everyone should have edit capabilities. There's actually if you click the arrows, there's actually 3 pages for you to put things into with 3 different questions. And then if you want to put something, you click on it's the sticky note here, and then you can type whatever your comment is. In my case, I thought of lots of wonderful ideas as I was listening to the talks today. And what's needed to facilitate my use of these data sets is more hours in the day. So I'll put that in as my sticky as an example. Of course, we probably can't fix that from the ESPWG side of things, but hopefully there's some things that will help to facilitate your use that maybe we can do as part of ESWG. So I'm going to set a little timer for like 3 minutes. And so if you'll spend the next 3 minutes putting in your sticky notes for each of the 3 questions. And then we'll discuss them after people have started putting them in. And of course, you can keep putting them in after the 3 minutes or even after the meeting, but we'll go to discussion after 3 minutes. All right, that's my 3-minute timer going off. We'll start with this first question: what's needed to facilitate your use of these data sets? And I see, other than my request to do something on physical, there's a number of requests related to making it easier to work with the data sets. I see notebooks that readily read in the data, information on available data sets, and I see here individual diagnostics versus community-based packages. Does whoever put that want to give a maybe explain a little more what you mean?
That was me, and it was sort of my hope would have been that so I have a lot of people who, no, that's exaggerated. I have some people who want to use the package and then they use it and then they do something, but nothing comes back. And so and it makes sense that if you want to diagnose a data set, I think it's a basic diagnostics problem. It's much easier if you use sort of the diagnostics package of your choice and you hack your code and then you get your result and you write a paper. And then if you actually go back and you contribute to these community-based packages, that is extra work on your side. And the community, there's some people really good about it and they're really technically strong. And there are some people for whom this is really hindering. And so speaking for myself, I run into the problem that I would like to do more. I would like to have more capability, but I only have, half an FTE working on that. And so some of the requests that come, we just can't do because we don't have, these are all external resources. And so I think this is a basic diagnostics problem, but I think it also is reflected for this ESP group of people, which need a different set of diagnostics than the standard climate diagnostics.
Okay, so I think what you're calling for is some support in providing that so that what people do diagnostic-wise feeds back into toolkits and software that make it easy for us to share with each other, basically.
Great summary, thanks.
Yes, and I think this is really exacerbated with with initialized hindcast data sets because they are, I think, there's a complexity there because of additional dimensions and things that I think really calls for providing more support and help in terms of making the data sets easier to use and then also sharing what we've done to make it easier to advance the science. I see a request for drift correction already applied to the output, and I also see a request for a training opportunity. Is there anybody else who has a comment or something they'd like to say about facilitating the use of the data sets? How can we, as a working group, try to better facilitate your use of these data sets? You can raise a hand, or you can put in a sticky, or you can write in the chat window. Yaga, go ahead.
I would like some clarification about the graduate student training opportunity. So I think at NCAR, we are more than happy to mentor additional students. So we're often on thesis committees, etc. So that's not a problem if you need ideas for thesis projects. I guess I'm not sure what is needed. Is it that we need ideas and connecting, or maybe whoever put that in can clarify what's missing? Is a hand by Yoshi.
Yes, so I just put that one. So in the graduate student, sometimes student is well educated, but sometimes they don't know how to analyze data, particularly for hindcast experiment, because hindcast require drift removal, also need a couple of adjustments, and then we have time dimension for the two, like real observation time, and also lead time. And then observation and the model have different grid, so they need regridding. So I know we need many kind of professional tool we require, but if there are some, based on the student level, if we have several, like for level 1, start from Python or something, level 2 for more analyzing the model, particularly like a regridding or something, and level 3 for hindcast experiment. If such kind of stuff, we available would be pretty useful. But of course, it's also university duty to train students. So I'm not sure this is appropriate to put in here, but if we can share some information about training students, it would be pretty great. So this is what I thought.
Yeah, thanks for that. I would say that I know that the work that Judith has done and associated and Anish and others with the S2S summer school and then and the Python package, I think is a really nice step in that direction and a great contribution. And I think what I hear you calling for is that we need to continue that and make sure that we continue those kinds of opportunities.
Yeah, so yeah, currently NCAR is huge effort, so I really appreciate that one. And then I really appreciate if keep doing summer school activity, also tutorial put on the YouTube or something. Those are pretty helpful. So yeah, thanks.
All right, thank you. I see another something in here that's some list of small diagnostic to-do projects for undergrads, i.e. what do co-chairs or others at NCAR like to see done, but don't have the time or resources. And I think what I see there is sort of, if we sort of the idea of a GitHub issues or to-do list kind of thing that might be helpful to so that people know how they can contribute in maybe small chunked ways, given the amount of time they have. But if somebody who wrote that would like to speak to that, feel free to speak up.
That was me, Kathy. This is Andrea, believe it or not. And this isn't so much, this is what I would like to see, but I know that professors who are looking for undergraduate projects are always contacting us with this kind of stuff. What would be a good project? What would be useful? What could somebody do with Merit 2? That kind of stuff. Little isolated projects that undergrads could tackle. They're all into the GIS and the machine learning and all this kind of stuff. And so they're always looking for ideas. So I just toss this out there as something that maybe could be useful here too. Sorry.
Great. Thank you. No, that's all right. We're getting low on time, so I'm going to move to the other two questions. You can still add to the board for later review if you'd like. So what is needed to facilitate volunteering to run experiments? And I see clear instructions and recipes for setting up initial conditions in a way comparable to existing hindcast sets, computational support from experts at NCAR Fizzle, list of specific gaps in analyses and volunteer solicitation, more hours in the day, funding for students, postdocs to run experiments. Yeah, I'm going to +1 that, or maybe +10 that one. And I see someone who's agreed to volunteer for the land Climo run. And so if that person would like to identify themselves so we know how to get who to contact, please speak up or put your name in the chat window or something.
Yeah, this was Sanjeev. Because I did a similar experiment maybe a year ago that got completed. So
great, thank you so much, Sanjeev. I'll be in touch, and mostly we just need help with creating the initial conditions. I think we can probably run the suites once we have actually the initial conditions. So I'll be in touch.
Thank you.
All right, and I'm going to go to the last question, and then we can discuss these last two at the same time. How important is the ability to run initialized hindcasts to you? And it's really a sense of whether people want to see data sets provided by the working group, or if people want the working group to help facilitate their ability to run initialized hindcast experiments themselves. And so I see somebody says moderate could be good for sensitivity studies, and moderate certain questions arise at times, and it would be nice to be able to test hypotheses. So I'm getting a sense that there are some people who want to be able to run initialized hindcasts. So in our last 4 minutes, if there's anyone who has a burning comment or question related to our discussion, now is your opportunity to speak up. So raise your hand or put something in the chat window.
And I'll also ask if you think we should be running experiments that we're not running and we should try to fit them in the next year. Please also speak up or send Steve and I or Kathy an email.
All right, I'm hearing silence and I'm seeing no hands.
And I'll answer a question from just came to me in the chat that yes, all the presentations and the recordings will be available. So if you didn't manage to write down all the links that were in the PowerPoints, Elizabeth is going to ask all the speakers to collect those. And I imagine then she's going to email the links out, or eventually they will be on the CSM website under the working groups. And I see Maria has a hand up.
Hi, so I put in a sticky on the second question that was asked, and it was about providing a list to solicit like volunteers for specific analyses. And so I just wanted to give kudos to Steve for doing that with the recent SMILE draft that you mentioned will be submitted sometime this week or so, but that was really neat, right? So there were subtopics that were listed and then people volunteered, and that just made it much easier to pick a subtopic that we're really interested in and provide some, targeted work hours towards something that we knew would contribute to a bigger project. So, so kudos for that. And I'd love to see that done some more.
Thank you.
Thanks, Maria. And I wanted to jump in and just mention on the topic of diagnostics that along with the SMILE paper will be a pointer to the GitHub repo that was used to generate all the analyses in that paper. So all the plots that I showed today, and that repo, was developed collaboratively. It uses Pangeo tools, it uses Dask, and I think that repo might begin to address some of the issues of data intake, which I see as the real bottleneck for analyzing hindcasts. Is how do you get the data from disk into your notebook or whatever platform you're using? That's a huge task, and so we're trying to develop a more formal intake ESM that's specific to initialized prediction with help from their ESDS group. And I think that's a pretty high priority for this group moving forward.
All right, and I also saw Isla had a hand up earlier. Isla, did you, I don't know if that was on purpose or I overlooked you, I apologize.
Yeah, no, I took it down because it was kind of on the board, but I was basically going to say what Steve just said, which is that Steve's got all these really nice notebooks, which I think maybe it could even become more of a kind of tutorial that kind of helps people to understand the like basic pieces that are in those notebooks that would help people. I find it really useful to follow some of what Steve did in trying to read in the massive amount of data quickly. So yeah, basically what Steve just said.
All right, thanks. All right, we are at 2 o'clock, so I'm going to pass it back over to Yaga and Steve, and if there's any last comments before we call it a day.
I think that's all I have. Thank you everyone for coming. We really appreciate you taking the time, and send an email if you have any questions. And Steve, do you have anything else?
No, that's it. Thanks everyone.
Thanks everybody. Thanks speakers.